the very last thing I'm going to go over is a new definition for acids and bases, and that's the Bronsted-Lowry acid-base definition. So a Bronsted-Lowry acid donates a hydrogen ion, while a Bronsted-Lowry base accepts a hydrogen ion. So that's a good way to remember that. It's the bad rule. Bases accept while acids donate hydrogen ions. So now we don't have the obvious acid producing H plus with a base producing OH minus that we had with the Arrhenius definition. Instead, we're going to be talking about hydrogen ion gaining and hydrogen ion loss. Okay, so if you look at this example right here, you have NH3 reacting with water, ammonia reacting with water, and it produces ammonium and hydroxide. Ammonia is going to act as the base because if you look, ammonia goes from NH3 to NH4+, which occurs because it accepts a hydrogen ion. One key thing to note, since it is gaining a hydrogen ion, it becomes NH4+ because the hydrogen has a +1 charge. So while ammonia is the base, ammonium is going to be what we call our conjugate acid. Okay, so every base has a conjugate acid, every acid has a conjugate base. So ammonia is the base because it is accepting a hydrogen ion, becoming NH4+. Water is the acid. Notice water, because it loses a hydrogen, it had no charge to begin with, then it becomes OH minus because it lost that plus from the hydrogen ion. Therefore, while water is your acid, hydroxide is going to be your conjugate base. So let's look at some more examples of conjugate acid-base pairs. Okay, so HF, if HF is an acid, then F minus would be its conjugate base because HF lost its hydrogen ion and therefore it's going to have a negative charge, so it's going to become F minus. Now if water instead is acting as a base, it's going to accept a hydrogen, so it would become, instead of H2O, it's going to become H3O because it gained a hydrogen, and it will have a plus charge because it gained that hydrogen ion. All right? Let's look at another example. I have HCl plus OH minus produces H2O plus Cl minus. So I know the hydrochloric acid, HCl, and the chloride ion on the product side are going to be paired together. HCl to Cl minus, HCl lost a hydrogen ion, therefore it is going to be an acid, while Cl minus is its conjugate base. Hydroxide gained a hydrogen ion, so it's going to be the base to become H2O. Notice H2O doesn't have a charge because the OH minus, that minus charge was canceled out with the plus charge of H plus, and so water is going to be its conjugate acid, and that's it. So in the last video, we talked about being able to identify acids versus bases, and now I'm going to give you a quick introduction into how to quantitatively measure how much acid there is in the solution. And specifically what you're going to be using is the pH scale. Now you might have been exposed to the pH scale, the whole concept that if your pH is below 7, then you're going to have an acidic solution. If it's above 7, you're going to have a basic solution. And if it's at 7, then you have a neutral solution. Well, we're going to actually be able to calculate the concentration of hydrogen ions based on the pH scale now. So pH actually stands for power of hydronium, which is the same thing as saying hydrogen ions. And the reason why the pH scale is important is because the concentration of hydrogen ions we're going to be measuring is going to be very, very small. And what the pH allows you to do, the pH scale allows you to take really small numbers and makes them between about 0 to 14. So it makes them much more manageable. So a couple of formulas. Here I've got that my pH equals the negative log of my concentration of H+. All right, and we're going to be talking about how to get rid of that log in a second because it's going to require some Algebra 2 work that you guys might not have been exposed to, but it's totally manageable, okay? So that's your pH right there. Your pOH is the same thing except it's the negative log of your concentration of OH minus instead of the negative log of your concentration of H+. And then finally, your pH plus your pOH, that equals 14. Okay, so let's look at an example. So here I give you your concentration of H+, and I ask you to solve for your pH and your pOH. So what I'm going to do is I'm going to go into my calculator, And because my pH equals the negative log of my concentration of H+, I'm going to just plug that into my calculator. I'm going to hit negative log of 1 times 10 to the negative third. And what you get is 3. That will be your answer. Now, the only tricky thing about these problems is making sure you're rounding to the correct number of sig figs. So, for your concentrations, if I give you concentrations of either H+ or OH-, you are going to be looking at sig figs. So, however many sig figs your concentration has, that's how many decimal places your pH should have. So, since H+ has 1 sig fig there, I'm going to need to make my pH 3.0 so that it has 1 decimal place. Now, since I know that the pH plus the pOH equals 14, I can take 14 and subtract 3.0 from that in order to get my pOH, which is 11.0. Okay? Let's look at a slightly trickier problem. What if instead of giving you concentration of H+, what if I give you your pH and I ask for your concentration of OH-? Well, I can first determine my pOH. I just need to take 14 and subtract 2 from it, so I get 12.0. Okay. Now comes the part of getting rid of your log. So if you look at your formula for pOH, it tells you pOH equals the negative log of your concentration of OH-. So I'm trying to get OH- all by itself. So what I'm going to do is I'm going to try and get the log of OH- all by itself. So I'm going to move that negative sign over, and what that would give me in this problem would be negative 12. Okay, so negative 12 equals my log of OH-. Now to get rid of your log, all you need to do is you need to take 10 and you need to raise it to whatever that value was on your left-hand side. So in this case, it would be 10 raised to the negative 12. Because what you don't see here is the way that a log is actually supposed to be written is negative log of, and there's a little number between log and OH-, and then we call that base 10. So it's going to be 10 raised to the negative, whatever my pOH is, that's going to give me my concentration of OH-. So that's the hard algebra 2 part of this. If you don't want to remember that, just always remember, if I'm trying to solve for either H+ or OH-, I'm going to take 10 raised to the negative either pH or pOH, and that's all you have to remember. So here, I'm going to take 10 and raise it to the negative 12.0, okay? I want, because my pOH has 1 decimal place, I want 1 sig fig in my final answer, so what I would get is 1 times 10 to the negative 12, and that's my answer. Now, this works out perfectly because my pOH and my pH are whole numbers. What if they're not? And they're not going to be in some of the practice problems you guys are doing. Well, all you would need to do is take 10 raised to the negative whatever your pOH is or whatever your pH is, and then figure out how many sig figs your answer needs. So if I got, for example, 1.8 times 10 to the negative 12 for my answer, I would just round that to 2, so my answer would be 2 times 10 to the negative 12, and that would be my concentration of OH-. Okay?